Beneath scarred earth, machines as tall as office blocks and as heavy as warships tear through the ground day and night, moving mountains at a scale few can imagine. In operations where a single bucket dwarfing a car bites off tons in seconds and arms longer than stadiums sweep above crews, one failure can unleash chaos measured in lives and fortunes lost. This is not science fiction. These monstrous machines are real, their dangers constant, and their existence strains the limits of what should be possible. What does it take for human engineering to create forces like these, and what happens when control slips? The truth you will see here will change how you think about the world beneath our feet. At the edge of open pit mines, an engine hums with the patience of geology. The Bagger 288, a bucket wheel excavator, towers nearly 100 meters above the ground. Its rotating wheel alone spans 21.6 meters, wider than a 4-lane highway. Each of its 18 buckets, carved from steel, can scoop over 6 cubic meters of earth in a single pass. This machine does not pause. Every minute it devours tons of overburden, clearing space for coal seams hidden beneath. In a single day, it can move more earth than entire construction fleets manage in months. The ground shakes as a frame weighing 13,500 tons creeps forward on 12 caterpillar tracks, each nearly 4 meters wide, distributing its colossal weight so evenly that it can cross fields without leaving deep scars. In 2001, the Bagger 288 faced a challenge as daunting as any seam of rock: a full relocation intact from the Hambach mine to Garzweiler, 22 kilometers away. Dismantling was ruled out because reassembly would take months and the cost would rival building a new giant. Instead, engineers charted a path across highways, rivers, railways, and farmland. The journey took 3 weeks. Crews reinforced riverbeds with steel pipes, laid gravel over roads, and even seeded grass to protect fields as the tracks advanced slowly. At every crossing, teams worked day and night to guide the machine's 220-meter boom and massive wheel, balancing tons of steel above fragile bridges and power lines. 70 workers managed the move, maintaining safety protocols as the Bagger inched forward at less than a walking pace. Overhead, the rotating wheel loomed, a constant reminder that this was a force, not just of industry, but of will, relentless and unstoppable, and always hungry for more ground. Hydraulic excavators operate in a realm where brute force alone is never enough. Precision is the currency here, and the stakes are measured in tons of rock balanced on the tip of a steel arm. Machines like the XCMG XE7000 and the Terex RH400 are engineered to carve through hard seams where a single miscalculation can cost hours or lives. Their arms stretch nearly the length of a stadium, reaching over 20 meters to extract material from ledges where other machines cannot risk a misstep. Each move is governed by a complex network of hydraulic cylinders, thick as tree trunks, pulsing with oil under pressures that would crush a car. Inside the control cab, operators command this power with the touch of a joystick. The response is immediate but never reckless, and micro adjustments in the flow of hydraulic fluid can shift a bucket weighing over 20 tons with the accuracy of a surgeon. These machines are built for reliability, with twin-engine configurations that guarantee backup power. If one prime mover falters, the other keeps the operation alive, preventing catastrophic downtime in environments where every minute counts. The bucket capacity on these giants can exceed 40 cubic meters, enough to swallow a pickup truck whole. Yet it is the balance between raw force and delicate control that defines their legacy. Engineers face a constant trade-off, deciding whether to reinforce the arm for strength or to lighten it for agility. Every weld and hydraulic hose is a calculated risk, tested by the relentless cycle of loading and dumping. In this world, redundancy is not a luxury, it is the difference between a seamless shift and a multi-million-dollar standstill. These machines reveal the limits of what precision can achieve at scale, and they set the stage for even larger feats of earth moving that follow. Draglines rule the horizon of strip mines, their booms rising like steel spines against the dust. Assembling one of these giants is a feat of choreography and patience. Each boom segment, some stretching longer than a city bus, arrives by convoy and is lifted into place with precision cranes. Workers bolt and weld the lattice together piece by piece until the structure rivals the length of a football field. The house-sized bucket dangles at the end, suspended by cables thicker than a man's arm, each strand inspected daily for frays or stress marks that could spell disaster. When the time comes to raise the boom, the entire crew gathers. Massive hydraulic jacks and winches haul the lattice skyward inch by inch as spotters check alignment and tension. The ritual is measured and tense. One miscalculation, one overlooked bolt could send thousands of tons of steel crashing down. Once upright, the dragline's boom sweeps in slow arcs, reaching deep into the earth to drag up hundreds of cubic meters of overburden with each cycle. The bucket alone can engulf a small car, and it swings on cables that must withstand shock loads every minute of every shift. Operators and ground crews work in constant awareness of the danger. Every shift begins with a walk down along the boom, eyes scanning for cable wear, loose pins, signs of metal fatigue. Inspections run like clockwork. Every cable, every joint, every hydraulic system checked and logged before the first load is moved. The dragline's power is cyclic and relentless: dig, swing, dump, return. Each cycle moves more earth than a fleet of trucks could haul in an hour. This is the unseen ballet that primes the mine for the next phase, hauling away the mountains of material these machines lay bare. A front-end loader stands at the pit's edge, its bucket poised like a steel jaw. The Komatsu Litorno L2350 is the world's largest of its kind, 260 tons of articulated muscle with a single scoop capacity close to 40 cubic meters. In one motion, it swallows enough rock to fill a city bus, then pivots to feed the waiting haul truck. The loader's tires alone are taller than most adults, each rotation grinding dust into the earth. Efficiency here is measured in cycles per minute, one bite, one truck, then back for more. Around the clock, the rhythm continues, with each bucketful keeping the mine's lifeblood moving. But this relentless pace depends on more than just brute force. The loader's hydraulic systems, pumping oil at pressures that would flatten a car, require constant vigilance. Maintenance crews move in as soon as the machine pauses, checking for leaks, swapping out filters, and monitoring wear on the massive pins that anchor the bucket. Every few weeks, the hydraulic cylinders are rebuilt on site, a process that unfolds with surgical precision under floodlights. Technicians work in teams, their hands blackened by grease, racing the clock to keep downtime to a minimum. It is a battle against fatigue, both mechanical and human. The loader returns to its post, bucket lowered, ready to deliver another one-bite load. In this world, uptime is everything, and the silent choreography between operator and crew keeps this giant feeding the trucks, hour after hour without rest. A mining haul truck idles at the bottom of a pit, its shadow stretching across the dust as if to warn anything in its path. Machines like the Bell AZ 757 Tau and Caterpillar 797F are monstrous, built for one purpose: to move mountains, one payload at a time. The Bell AZ 75710 stands nearly 8 meters tall and stretches over 20 meters long, and its empty weight alone exceeds 400 tons. Each load piles on another 450 tons, enough to match the combined weight of 6 fully loaded passenger jets. The truck's diesel-electric drive system powers 4 independent electric motors, one for each rear wheel, channeling more than 4,600 horsepower through a dual-axle configuration. This design is not just brute force. Dual-axle steering geometry allows a truck the size of a house to corner on haul roads, barely wider than its own frame, while specialty tires, each over 4 meters high, are cast in a single foundry, shipped by convoy, and replaced every few months as they grind against rock and steel. Inside the cab, operators sit above a forest of hydraulic lines and high-voltage cables, eyes level with the rooftops of nearby buildings. Every ramp climb and sharp turn is a test of balance and control. Safety margins are engineered into every system with dynamic braking, redundant steering, and tire pressure sensors, guarding against disaster on steep grades. Supply chains stretch across continents, with each tire and axle custom built for the demands of a specific mine. When these trucks roll, the ground answers. They carry not just ore, but the weight of entire economies, and when something fails, brakes, tires, or steering, the consequences are measured in lives and millions of dollars lost. In this world, moving mass is an act of precision, and every journey is a reminder of how close power and risk can run. A 360-ton mining haul truck crests the rim of a pit, brakes hissing under the weight. The descent ahead is long and steep. Every system is pushed to its limit. On a cold morning in Canada's oil sands, a Caterpillar 797F began its run down a loaded ramp. The operator eased onto the brakes, but something was wrong. Hydraulic fluid, contaminated by months of dust and moisture, had begun to boil. Pedal pressure faded. The dynamic retarder, designed to slow the truck electrically, overloaded and tripped offline. The truck's speed climbed past 40 miles per hour, far beyond safe limits for a rig this size. At the bottom of the grade, an escape ramp waited, engineered as a last resort, lined with deep gravel berms to arrest runaway giants. The driver steered hard, tires biting into the gravel. The truck shuddered, plowing to a halt within meters of disaster. Investigators later traced the cascade to a single maintenance lapse in brake fluid checks, compounded by the relentless strain of heavy loads and steep gradients. Across the industry, escape ramps like this save an average of 8 runaway trucks each year. The incident triggered a redesign with cooling protocols for brake fluids, stricter diagnostics, and reinforced berm specs. Each layer of protection is a lesson written in steel and gravel. When machines grow this large, a single failure can multiply in seconds. The logic of safety is built on margins, every system backed by another, every risk anticipated, every escape route prepared before the descent begins. At the heart of every mega crane, balance is everything. On a crawler crane like the Liebherr LR 13000, lifting a reactor vessel weighing 1,600 tons is not just brute force. It is a battle against gravity, won through counterweight. These cranes are engineered with modular steel slabs, each weighing dozens of tons, stacked methodically onto the rear platform. The sequence is calculated down to the last kilogram. As the luffing boom rises, engineers monitor the shifting center of mass, adding or removing plates to match the load's arc. Too little counterweight and the entire machine could tip, even with a ring-shaped track spreading the pressure across a field. Too much counterweight and the undercarriage strains, risking structural failure. The counterweight system is not fixed. It adapts to each lift, sometimes requiring hundreds of tons to be trucked in and assembled on site before a single pick is made. Each slab is locked into place with hydraulic pins, their positions tracked by onboard sensors. During a lift, the operator watches digital readouts, ensuring the counterweight slides along its rails in perfect synchrony with the boom. This choreography allows the crane to reach further and higher, hoisting monstrous loads that would otherwise be impossible. The modular concept means that after the job, the entire counterweight stack can be broken down and moved to the next site piece by piece. In this world, balance is not an abstract principle. It is a physical reality measured in steel, sweat, and the relentless logic of physics. A floating heavy lift barge drifts into position beneath a waiting bridge section, its deck bristling with winches and cables. Here, the clock runs not just on manpower, but on the moon itself. Every operation is mapped against the tide chart, a narrow window when water and wind align just long enough to attempt the lift. Crew members check barge trim, adjusting ballast tanks by the ton to keep the platform level as the tide swells and recedes. Even a half-degree tilt can jeopardize a 2,000-ton load suspended overhead. On the dock, a port gantry crane stands ready, its rails stretching the length of a container terminal. These machines move with a rhythm dictated by global demand, each cycle planned to the second, throughput measured in boxes per minute. The largest ship-to-shore cranes, like those at Rotterdam or Shanghai, can hoist containers weighing over 60 tons, swinging them from ship to stack in under 2 minutes. The boom extends more than 60 meters, clearing even the widest hulls. Redundancy is engineered into every hoist and cable, with backup winches ready to take over if a primary line falters. Slew timing is critical, and operators monitor wind and tide in real time, halting movement if conditions drift outside the safe envelope. A single miscalculation, one gust or one surge, can force a shutdown, stranding cargo, and costing millions in lost throughput. These machines are the gatekeepers of trade, their scale matched only by the precision with which they must operate. In this environment, every lift is a negotiation between power, timing, and the unpredictable pull of the sea. On July 14, 1999, a crane known as Big Blue stood over the Miller Park construction site in Milwaukee. Its 567-foot boom stretched high above the stadium's rising skeleton. That afternoon, wind gusts swept across the open structure, The crane was rigged to lift a 450-ton roof section, an operation that had become almost routine for crews working with one of the largest tower cranes ever assembled in North America. But the weather did not care about routine. As the load swung out on the 400-foot jib, crosswinds reached 18 to 20 miles per hour, pushing against the suspended steel. Without an anemometer in use and with warnings unheeded, the lift pressed forward. Suddenly, the boom began to buckle. The massive load, now acting like a sail, caught the wind and shifted the crane's center of gravity beyond its tipping point. In seconds, thousands of tons of steel twisted and snapped. The 450-ton roof panel and the crane's upper sections crashed nearly 300 feet to the ground, crushing 3 workers below. Construction halted. OSHA investigators arrived to pick through the debris, tracing the failure to a miscalculation of wind load and a lack of real-time wind monitoring. The aftermath rippled far beyond Milwaukee. New codes demanded wind sensors on every major lift, stricter limits on operation in gusty conditions, and updated engineering standards for dynamic wind effects. Today, every crane operator studies the lesson written in the wreckage of Big Blue, that the invisible force of wind, if underestimated, can turn even the most powerful machine into ruin. Deep beneath city streets, a tunnel-boring machine spins its cutter head, a steel disc the size of a small house bristling with tungsten teeth. Each revolution grinds through packed earth and fractured rock, carving a void wide enough for a subway train. The cutter head's diameter can exceed 17 meters, dwarfing the trucks that deliver its segments. Every piece arrives by convoy, each weighing as much as a city bus, craned into place and bolted together in the launch shaft. Once assembled, the front shield alone can press against the tunnel face with more than 400,000 kilonewtons of force, holding back the weight of the world above. Slurry and earth pressure balance machines work in tandem with the ground they conquer. In soft soils or beneath rivers, a pressurized mix of bentonite and water fills the chamber behind the cutters, matching the external ground pressure, often holding at values between 1.5 and 2.5 bar. If the pressure drops, the face can collapse, flooding the tunnel. Too much pressure in the ground heaves, threatening buildings above. It is a constant balancing act, monitored by a logistics manager who tracks every cubic meter of spoil, every ring segment, every pressure gauge. Behind the cutter head, a mobile factory inches forward. Ring segments, each weighing over 10 tons, arrive in a precise sequence, lifted and locked into place to form the tunnel's lining. The backup train stretches for hundreds of meters, loaded with grout, rails, and spare parts, all feeding the relentless advance. Every hour, the team faces the unknown, shifting geology, rising water, and the ever-present risk of a blowout. In this world, progress is measured in meters per day. Each advance a victory over the unseen forces pressing in from every side. At the threshold between mine and sea, the stockpile is a living mountain, fed by endless convoys of haul trucks, shaped by loaders and tamed by machines bred for scale. Here the first challenge is brute reduction. A primary crusher with a mantle weighing up to 120 tons and spanning nearly 3 meters across swallows boulders the size of cars with each cycle. The roar of steel against stone is relentless. In a single hour, the crusher can process more than 8,000 tons of raw ore, reducing blocks that once dwarfed men into fragments ready for the next journey. The crushed ore flows onto miles of conveyor, building stockpiles that rise and fall with the tempo of global demand. When the call comes from the harbor, another giant takes command. The shiploader boom stretches over 45 meters, longer than a blue whale, reaching across the yawning holds of bulk carriers. Its capacity is measured not in buckets, but in thousands of tons per hour. At peak, a modern shiploader can deliver 16,000 tons of ore onto a waiting vessel every 60 minutes, enough to fill a Panamax ship in less than a day. Every movement is orchestrated for maximum throughput. Slew drives rotate the boom with precision, trimming the flow to balance the ship's load. Operators monitor wind, tide, and cargo density, knowing that a single miscalculation can halt operations or risk a catastrophic spill. In this world, the scale of the machines is matched only by the stakes, a seamless chain from mine to ocean where failure is measured in lost millions, and the rhythm of global trade is kept by steel, stone, and the relentless drive to move more, faster. Night descends on a stretch of highway, but the work is only beginning. The tandem pavers roll forward in perfect alignment, their headlights cutting through the darkness as they lay down fresh asphalt lane by lane. Each machine is engineered for relentless efficiency. Massive hoppers feed heated mix into a screed that spans the width of an entire roadway. In a single pass, these giants can pave a strip wide enough for 4 cars to drive side by side, eliminating the seams and weak points that once plagued older roads. Crews move in a synchronized rhythm behind the machines, checking surface temperatures and compaction, while rollers follow close behind to press the new surface smooth. The scale is easy to miss until a worker stands beside a paver's conveyor, his helmet barely reaching the midpoint of the steel frame. On multi-lane highways, the operation unfolds like a time-lapse ballet. One shift can transform a battered road into a seamless black ribbon stretching for miles. During overnight cycles, the goal is to minimize disruption. Entire intersections are rebuilt before dawn, traffic returning to a surface that was rough gravel only hours before. Precision is everything. Modern pavers use laser and GPS controls to maintain exact thickness and slope, ensuring water runs off instead of pooling. The margin for error is measured in millimeters. When the sun rises, the evidence of the night's work is almost invisible, a flawless stretch of highway ready for the day's first rush of traffic. These machines don't just build roads, they shape the arteries of modern life, one perfect lane at a time. On the steep slopes where forests meet the limits of machine endurance, a different kind of giant takes command. Forestry harvesters engineered for extreme gradients must balance on inclines that would send lesser equipment sliding into ruin. Their undercarriages are widened, tracks fitted with high traction cleats, and hydraulic systems tuned to keep the boom steady even as the ground gives way beneath them. Remote operation is standard. Operators guide these machines from a safe distance, watching as massive steel arms grip and shear trees in seconds, clearing access for power lines or fire breaks where human crews cannot safely tread. Slope stability is a constant threat. A miscalculation in weight distribution or a sudden shift in soil can tip a 56-ton harvester with little warning. Designers test every weld, reinforce every pivot, and install emergency cutoffs to prevent catastrophe. In landscapes scarred by more than nature, another breed of machine rises to the challenge, the high-reach demolition excavator. Nowhere is the need for precision and distance more absolute than at the Fukushima Daiichi nuclear site. Here, a 65-meter boom, longer than a city block, extends into the radioactive shell of a ruined reactor. The engineer behind this custom extension, Tadashi Nakatsuji, lost family to the 2011 disaster. He pushed for a design that could dismantle steel and concrete from outside the lethal core, using hydraulic extensions, shielded by lead, and operated entirely by remote control. Each movement is deliberate, each cut monitored by cameras and sensors, as the machine reaches deeper into the heart of contamination. The boom's length is not just an engineering feat, it is a barrier between life and invisible danger. Hydraulic extension cylinders, some as thick as oil drums, power the arm's slow advance, their seals and lines checked daily for leaks that could cripple the operation. Both in the forest and the fallout zone, these machines are built for conditions where failure is not an option. They represent the edge of bespoke engineering where the terrain is unpredictable. The risks are measured in seconds, and the only certainty is the need to keep human lives out of harm's way. Far from the dust and thunder of open pit mines, the scale of heavy machinery takes on new forms, across oceans and even beneath the sky itself. On the deck of a pipelay barge, a crane rises above the rolling waves, its slewing ring engineered to rotate thousands of tons with the precision of a watchmaker. These offshore giants are built to place wind turbine foundations and lay pipelines on the seabed, where the line between stability and disaster is measured in degrees. Ballast tanks below the waterline shift by the minute, counterbalancing every movement as the crane's boom swings out over open water. Even a modest swell can set a 2,000-ton load swaying, so crews monitor heel and trim constantly, adjusting ballast with the urgency of a ship's captain in a storm. The barge itself becomes a floating foundation, engineered for moments when a single miscalculation could send steel and cable crashing into the sea. But the boundary of what humans can move does not end at water's edge. At NASA's Kennedy Space Center, the crawler transporter waits in silence, its twin tracks stretching 18 meters wide, each link the size of a compact car. Originally built in the 1960s to carry Saturn V rockets and later the space shuttle, this behemoth tips the scale at 2,721 metric tons. Its diesel-electric engines churn out thousands of horsepower, but speed is a luxury it cannot afford. The crawler advances at just 2 kilometers per hour, rolling beneath its cargo with a steadiness that belies the weight above. Hydraulic jacks, mounted at each corner, adjust the platform in real time to keep a rocket perfectly upright as it travels from assembly building to launch pad. The smallest tilt, a fraction of a degree, could spell disaster for a mission years in the making. On land or sea, these machines exist at the intersection of brute strength and delicate balance. Offshore cranes must tame the motion of the tides, while the crawler's tracks flatten the very earth beneath the world's most ambitious launches. Each system is a study in extremes, slewing rings built to withstand hurricane-force winds, hydraulic jacks that level thousands of tons with a whisper, and tracks so wide they could swallow a city street. In these realms, scale is not just a matter of size, it is the art of moving the impossible, one measured step at a time. Every day, monster machines move 100 billion tons of earth, more than all rivers combined. As global demand for resources and infrastructure explodes, these giants push the limits of what is possible and what is safe. The world we build depends on their power and the risks we accept to wield it. Respect the scale, question the cost. If these machines amazed you, share your thoughts below.